I'm going to teach. So here's what Calc 4 is. Calc 4 is like learning 150 different approaches to different differential equations. And I'm going to teach you one of those. The first one possibly that they'll teach you in Calc 4, separation of variables.
Oh, the easiest.
The easy one. The easy. I'll teach you the easiest first one, and then you can relax while they're teaching you that, but then the rest you'll have to pay attention. Okay, so I'm not going to really go through the syllabus again because we just did that and it's exactly the same, but I will show it to you first. So this class is called Deformable Body Mechanics, or DEFORM. Let me, most universities call it Mechanics of Materials. So if you ever look at a university you're thinking of transferring to and you see Mechanics of Materials, that's this. We call it DEFORM because that's what the U of Minnesota calls it, but that's pretty unusual name for it. You can see in this background picture, that's a finite element analysis printout or graphic. What we're doing in this class is, some very simple applications, calculations in very simple setups of the same stuff that you would use finite elements for, if you've ever heard of finite elements. We're going to be talking about stresses and strains. And so, yeah, really, like how many companies have you do stress and strain calculations by hand instead of using finite element packages? 0.0%, and that's rounded up. But what we're going to do in this class is I'm going to, introduce you to what stress and strain are. And then that understanding is really what you're going to carry forward when you start dealing with, finite elements or whatever. Also, it seems to be the case. So I teach this class in sort of an unusual way. I do it all with matrices. And stresses I present as these things called stress tensors. That's not the usual way that this is taught, but for the people who transfer to the University of Minnesota, at least the people in aerospace, and I think a lot of the people in mechanical engineering too, are required to take a class eventually where they're like, oh, well, you learned stresses and strains this way, but now we're going to show it to you in this matrix and tensor form. And so the feedback I've gotten is that this just makes it a much easier transition when you go to the way that it's really done. We're sort of skipping the way it really isn't done and just going right into the way it really is done, Okay, so the syllabus. What's new? It's the same thing as in dynamics. I want you to just focus on what I give you in class. I don't want you to use outside materials. You can, but you'll find it really just confuses things more than it helps. So if something's confusing in class, come get it clarified with me or talk to each other about it. I think you'll be much happier with the way that works than trying to look for YouTube videos or something that teach it in a different way. The topics we're going to do, so I'm going to first talk about matrix math. We're going to start with a vector review. Since all of you are also taking dynamics, I'm going to assign vector problems in both classes, and they're the same ones that you did in statics. Okay, that seems like a lot of the same problems. For the people who are taking dynamics and deform, just turn them in for one of those two classes. But as far as the people who took statics and have to do it again, like tough luck, do it again. You'll remember it better. Sort of the heart of what we're going to be dealing with is the relationship between stress and strain. You can think of stress as the loading at an infinitesimal, at like a point in the material, and you can think of strain as the deformation of that point in the material. And there's a relationship between those two that's called the constitutive relationship. And so a lot of what we're doing is figuring out, if you know this about the stress, what do you know about the strain? Or if you know this about the strain, what do you know about the stress? And we'll talk about some mathematical stuff like, okay, what if you know the stress in a coordinate system like this? What is the stress in a rotated coordinate system? You've done that kind of stuff with forces before, like with inclined planes in physics 1. You know, if you have a box that's sliding up or down an inclined plane, you know that the weight force vector is straight down. Well, it turns out it's easier in a lot of ways to use a rotated coordinate system. So one thing you had to do was figure out what that weight force vector is expressed in a new coordinate system. Okay. The analogous thing for deform is, you know what the stress tensor is in one coordinate system. What is it in a new coordinate system? So that's transformations. And then, you know, most of what we're going to spend our time on is for an actual loaded material. So say you have a beam that has this internal load, set of internal loads on it. What are the stresses and strains at different points? And we're going to talk about how to do those calculations. This is a really long list of topics, but that's kind of the main idea of it. And then at the end, we'll talk about column buckling. So if you just stretch a piece of metal until it breaks, okay, it breaks according to the stresses and strains that it can tolerate. That's not actually what happens if you have a pole and you press down on it. That's not just going to withstand that downward force until it fails in the typical, you know, until it just mashes down to the ground. Instead, it's going to bow out and fail in like a bending mode, okay? And that's column buckling. And so we'll talk about column buckling. And then we'll talk about stresses in pressure vessels. So imagine if you have a pill-shaped thing, like a cylindrical thing, or you have a spherical thing, and you have different pressures on the inside and the outside.
So a submarine?
Yeah, right. It was really cool teaching this class last year because everyone was into it because of that pressure vessel that imploded in the ocean. The what?
Ocean Gate.
Yeah, right. And so anyways, we'll talk about that and talk about different applications of it. The grading scale is 90, 80, 70, 60 or lower. You know, but usually this is what it'll end up being. I usually don't have to curve anything. And the grade breakdown is exactly like it was in dynamics, what it's going to be in dynamics. These are the schedule. This is the schedule for the exams. So, look at that schedule and see if you can make it. If you can't, we can make other accommodations. But really everything else is exactly the same as in dynamics. Anybody have any questions about the syllabus or the structure of the class? Yeah.
Can't tell, but are the exams the same week as the dynamics exams?
They're the same week, and one is on Monday and one is on Friday. Yep, that's right. Any other questions? Okay, well, let's get into a little bit of matrix math. So in dynamics, all of the mathematical preliminaries for the class are calculus related and differential equations related. In D-form, none of it is calculus related. It's just all matrices and stuff. So mathematical preliminaries. Matrix math. When something is a matrix, I'm going to write it, just like when a variable is a vector, you usually see it with an arrow over the top. When something's a matrix, I'm going to write it with an undersquiggle like that. Okay, so that means that something's a matrix. And I'm just making up a random matrix, but 2, 1, -2, 4, 0, -6. So say that's your matrix. You put it in square brackets. The size of this matrix, so to give the size of a matrix, you first give the number of rows, and then you give the number of columns. Okay, so how many rows are there? 1, 2, 3. So this is size 3 by, and how many columns are there? 2. So this is a 3 by 2 matrix. And if you're talking about the elements of the matrix, you give the element by the row that it's in, followed by the column that it's in. So element 1, 1. And a lot of times you'll write the elements. So a lot of times the matrix name will be a capital letter like this. And then for the elements, you'll just use that same letter but lowercase. That's a pretty common way that people write this. So what's the element that's in the first row and the first column?
2.
Yep, exactly. What's the element that's in the first row and the second column?
1.
Yep. Then the second row, first column is -2. Second row, second column is 4. Third row, first column is 0. And third row, second column is -6. All of our matrix calculations we're going to do in our calculators. I mean, it would be a horrible, horrible decision to do these. I mean, I'm going to tell you how to do these by hand, but you do not want to spend the class trying to do these calculations by hand. So how do you put these into a TI calculator? How do you put a matrix in a TI calculator? The first way is if you have a TI 83 or 84, then you have to go to hit the matrix button, which I think is like second function and then math. So go matrix. And then once you're in there, go to edit, and you can just fill out the matrix. It'll ask you the size. In this case, you would fill out 3 by 2, and then it'll give you that size of matrix, and you'll just punch in those numbers, 2, 1, blah, blah, blah. If you have a TI 89 calculator, there are 2 ways you can do it. In both cases, to tell it it's a matrix, you give it a square bracket at the beginning and the end. The first way is you go row by row, and inside these square brackets, you have more square brackets to define the row. And then inside the row, you separate the elements by a comma. So you would do this as like, so to do the matrix that I gave you above, is that right? 2, yes. You would go, okay, the first row is 2, 1. So you go 2, 1, and then end the first row. Okay. Then the second row is -2, 4. Then end the second row. And then the third row is 0, -6. Now that we're done with the matrix, give the closing square bracket, and that'll do it. Okay, a little quicker way to do it is a square bracket to say it's a matrix. And now use commas to separate elements along the row, and semicolons to go to a new row. Okay? Think of it as like the ding thing on an old typewriter, you know? That's the semicolon. So you go 2, 1, semicolon, -2, 4, semicolon, 0, -6, and then close the matrix. And the last way is if you have a TI Nspire, there is a button that looks like a matrix. It looks something like this. Okay, hit that, then it'll ask you what size you want, and then you just enter it with the keypad. This is pretty quick and easy and graphical. Well, first of all, does anyone have a graphing calculator other than a TI calculator? An HP or something? Okay. Well, after class, try to enter, make sure that you can get this working. What sizes of matrices are we going to deal with in this class? There are, what does it say? 4 matrix sizes. So there are 4 important matrix sizes for this class. The first one is a 3x1 matrix. That's vectors in 3D. That's what this is going to represent. And, you know, it looks like the vectors that we dealt with in statics. And forces are really the reason why this is important. So, for example, we might have a force vector that's equal to 10,000 in the x direction, negative 15,000 in the y direction, and positive 5,000 in the z direction. And this is all in newtons. So 3x1 means 3 rows, 1 column, so you just get a single column matrix like this. The second one is a 6x1 matrix, so a column matrix with 6 elements. This is, you don't know what this means yet, but this is going to come up, so this is your first time seeing it. The Voigt form of stress or strain. So for example, you might see something like this. So this epsilon is the symbol for strain. And you might see a strain value at a point that's like 1.5 times 10 to the minus fifth. Then 0, 0, negative 6 times 10 to the minus 6, 0, 0. And by the way, we'll see this later, but strain is unitless, so no units on this particular matrix. One thing you can see from what I wrote here is something that we'll see in this class. Any of the materials that we deal with in this class have very small strain values. So if you ever see a strain value bigger than about 1 times 10 to the minus fourth, that's not realistic for the approaches we're using. We'll still sometimes see it just as mathematical examples, but yeah. So start getting in the habit of thinking of like 1 times 10 to the minus fourth as being sort of an important cutoff for us for strains. Third is 3x3 matrices. And this is going to be useful for us for 2 things: stress tensors and rotation matrices. So for example, a stress tensor would look like this. The symbol for stress is the Greek letter sigma. So let's say that we have a stress tensor representing a single point in a material. And the values are 6 times 10 to the 6, 0, negative 8 times 10 to the 7. That's the first row. And then 0, then 5 times 10 to the 7, negative 2 times 10 to the 6. And then negative 8 times 10 to the 7. Negative 2 times 10 to the 6. Negative 5 times 10 to the 7. And that has units of Pascal, like pressure. One thing to notice for later is stress tensors are always symmetric matrices. So here's what symmetric means. If you sort of, as a reference, consider that diagonal going from the top left to the bottom right, okay? All of the elements are equal if you think of them as being reflected around that line, okay? So this is equal to this. This is equal to this. And this is equal to this. That's not true for rotation matrices, but that's going to be an important fact for stress tensors. And actually, the fact that the stress tensors are always symmetric is the reason that we can represent stress tensors in what's called the Voigt form here. Because how many elements are there in a stress tensor? 3 by 3 is 9, right? But if you have this property that the red ones are equal, the blue ones are equal, and the gray ones are equal, how many independent values do you have in a 3 by 3 matrix? 6. And so if you only keep track of the independent values, all this information can be stored in this 6 by 1 form, okay? And then last, and really this one right here is the reason that we need to do everything using calculators. The final important matrix size is 6 by 6. That makes calculations super, super time consuming if you're trying to do them by hand. And we're going to use 6 by 6 matrices for the compliance matrix. And also for the stiffness matrix. Well, as an example, the way that you calculate the compliance matrix is, so the first row is 1 over this value called the Young's modulus, the stiffness of the material, negative Poisson's ratio, that's the Greek letter nu, divided by the Young's modulus. The third element in the first row is negative nu over E. And then we have 3 zeros. Now we're on to the second row. And the way this works is for all of the first 3 rows, This is a first glimpse at this stuff. You don't have to remember this stuff after today. You're going to keep seeing this stuff. But the 1 over e just keeps moving along in these three, and the negative nu over e fills out the other two spots. So now we have 1 over e here, negative nu over e here, and zeros. The third row, we have 1 over e here, negative nu over e here, and 3 zeros. Now we're half done. And now for the 4th through 6th rows, we have this one element that's a little bit ugly, but it just keeps moving along. So we have, in the 4th element of the 4th row, we have 2 times the quantity 1 plus nu over e, and then 0, 0. For the 5th element, this moves over to the 5th spot. And for the 6th row, that moves over to the 6th spot. Okay, and that compliance matrix, so what you do is you take a material, say you're working with, you want to do calculations related to steel or copper or whatever. You take a strip of that material, the steel you're using or copper, you put it in a testing machine, you apply giant forces to it to stretch it a little bit, you measure what those forces are, you measure how much it stretches, and through a fairly simple method that we'll talk about in not too long, you can calculate the Young's modulus and the Poisson's ratio. Then based on that, you can fill out this compliance matrix that lets you determine the relationship between the stress at a point and the strain at a point. So if then, for example, you know what the stress is in a piece of copper at this spot, this matrix will let you calculate the strain at that point. Okay, so now we need a few definitions. So these are important matrix definitions. The first one is transpose. So if B, the matrix B, is the transpose of A, and you write it like that with it looks like it's to the power of T. Okay? Then every element ij of the matrix A is equal to the element ji of the matrix B. So you just switch which is a row and which is a column. Okay, so for example, if you have a matrix 1, 2, 3, 4, 5, 6. Then A transpose, if you switch, okay, so let's think of the elements of this. So this is A11, right? If you switch those two subscripts, it's still A11, right? So this is still going to be 1. But now in the matrix A, A12 is equal to 2, right? But if you switch those subscripts, now this is going to be A21 in the transpose matrix. Are you with me on that? So the 2 now would go here instead of to the right. In the matrix A, 3 is the element A21, right? You see that? So in the transpose matrix, it's going to be the element A12. So it's going to be here. In the matrix A, the 4 would be A22. That means that in the transpose, it's still going to be 2, 2. And if you do the same thing with these last two, you get the 5 and 6 like this. So what we got was a different size matrix where the things that used to be rows are now columns and vice versa. There are a couple things to notice about transpose. First, the transpose of an M by N matrix has the size, what do you think that's the answer is going to be there?
N by N.
Yeah, N by M. Second, it wouldn't be hard to write a program to do this, but every TI calculator has this as a built-in function. And it shows up as like a little t. And so if you enter a matrix into your calculator, and then like say you entered this matrix 1, 2, 3, 4, 5, 6, and then call up the function transpose, it'll spit out this matrix. Any questions about that? Okay, the next definition we need is a square matrix. And that means same number of rows and columns. For square matrices, we're going to use this naming, nomenclature. For square matrices, the diagonal elements are the elements where I is equal to j. You know, where the two subscripts match each other. Think about like a square. Let's go back to this one. I have it all marked up, but this is a square matrix, right? What I have circled here is the diagonal. Let's think about what those element numbers are. 6 times 10 to the 6th is element 1, 1. 5 times 10 to the 7 is element 2, 2. And negative 5 times 10 to the 7 is element 3, 3. Okay, so the diagonal elements are all the ones where those two subscripts match. Okay. On the other hand, you know, anything that's not diagonal is called an off-diagonal element. And those are the ones where A is not equal to J. Well, sorry, I is not equal to J. Yeah.
If you transpose a square matrix, like that one that's symmetric, will it be the same thing when you transpose it?
If you transpose, yes. A square matrix doesn't have to be symmetric. But if you have a symmetric square matrix, then the transpose is the matrix. That's right, exactly. That's like the definition. And I am out of notes here, but I think that's the last thing that I want to say is symmetric, a symmetric matrix. So you can only have a symmetric matrix if it's a square matrix. A symmetric matrix is a square matrix where the ijth element is always equal to the jith element. Or in other words, the matrix is equal to its transpose. Yep.
So it always has to reflect over those diagonal elements. It can't be like symmetrical over a different.
Right, correct. Yep, it has to be over that diagonal. And there's one more thing to keep in mind. How many of you guys have taken a class where you've used eigenvalues and eigenvectors yet? Anyone? Yeah. Oh, okay. A lot. It's going to start coming up in every engineering class right about now. This is kind of the beginning of it, just coming up all the time. There's applications of it for everything. And so what I want you to notice is symmetric matrices have all real eigenvalues. What that means is that if you have if taking the eigenvalues and eigenvectors of a matrix has some kind of physical meaning that you can express in terms of, say, newtons or, you know, some physical thing, that probably means that matrix has to be symmetric because, you know, an imaginary value of newtons of a force or something doesn't really have a meaning, you know what I mean? And so this relationship is something we're going to be taking advantage of in this class. Okay, any questions? All right, let's stop there. And next time we'll just keep going with matrix math, talk about multiplying matrices, and yes. And so for this and dynamics, be sure it won't be up for a little while, but this afternoon, just look on D2L and there'll be an assignment. Okay.